A very important element we want to consider in this course, Engineering Mechanics, is the beam. For the statics problems we want to deal with in the first half of the course, this is that we are interested in the internal loads. That means forces and moments which appear within the element of this beam and which we could calculate by cutting through this element, so make a free body diagram where we cut through the beam. Later on in the course, for mechanics of materials, we are only also interested in the elastic deformation that these internal loads cause. But right now, let's look at the beam problem itself. And I want to introduce this beam problem with a very simple example, the so-called simple beam, which has a pin bearing in the beginning at the point A and a loose bearing at the end at the point B. And in this case, I've introduced a typical coordinate system used for beams where we have the x-axis along the beam to the right, the z-axis downwards, and the y-axis is coming out of the plane. You can check by using your right hand that this is a positive coordinate system where the thumb is the x-axis, the middle finger is the z-axis, and then your forefinger will come out of the plane, which is the direction of the y-axis, and the direction of the y-axis gives you the positive sense of rotation if there are moments occurring. If we are interested, as already mentioned, in the internal loads of the beam, we have to make a free body diagram, so we have to cut through the beam. And of course, then we will get at least two parts of the beam, one left part and one right part. And we do not call them left or right part, but we are looking at the so-called cutting faces of the beam and how are the cutting faces defined. Here I made the free body diagram of the beam. And you can see we have on the left-hand side the so-called positive cutting face, because if we would enter here the normal to the cut face, the normal, which is pointing out of the material, points to the right, so in positive x direction, whereas on the left-hand side, the normal points in the negative x direction. And our definition is that if the normal pointing out of the material has the same direction as the x-coordinate axis, then this is the so-called positive cutting face, and vice versa, the other one is the negative cutting face. And going on with our convention, if we have identified the positive cutting face, then we say that all internal loads, so the normal force, the shear force, and the bending moment, have to be applied in the free body diagram in positive coordinate direction. That means the normal force N along the beam in positive x coordinate direction, the shear force Q in positive z direction, and the bending moment M in positive y direction. For the left part, so for the positive cutting phase, for the negative cutting phase, we have to include the internal loads in negative coordinate direction. That means normal force to the left, shear force to the top, and bending moment with respect to the negative y-axis. That means that in this free body diagram, the internal loads on the left-hand side, so on the positive cutting phase, and on the right-hand side, so on the negative cutting phase, fulfill the actual equals reactio principle. One further hint for the free body diagram: if you apply the external bearing reactions, so in A and in B, you would add here two forces in C direction, FAC and FBC, as well as one force in x direction, FAX in this example. And as we do not know the bearing reactions in advance, I would strongly recommend to apply them in positive coordinate direction so that you can apply the formulas you have learned about in the lecture. When we are talking about internal loads in our beam, we are interested in the results out of external loads. This can be discrete forces, discrete moments, or also line loads, which have an effect on the bending moment and the shear force function, as well as on the normal force function. The thing which is more complicated compared to the normal force, so the direction along the beam's axis, is the direction perpendicular to that, because there is an interaction between this distributed load which is acting on the beam. This could be some wind load, some snow load, which is of course not so important in Singapore, but in Germany there could be a relevance for snow loads as well. And this distributed load, which has the unit of Newton per meter, is somehow transferred to the internal load, the shear force, as well as the bending moment. There can be discrete forces acting on our system, and there can be discrete moments acting in our system. And the relation in c direction, so the relation between this distributed load function, the shear force function, and the bending moment function is as follows. First of all, we have some q of x, which is the line load function. And to get from the line load function to the shear force function, we have to integrate over this line load function. We can use a definite or indefinite integration scheme. In this case, I choose a definite integration scheme. So I start at the position x equals 0 and go to any position of the length of the beam at the position x and have to integrate over this line load function. Please keep in mind that for the line load function, this is the function given by the problem statement, and if I make the integration I have to flip the sign, therefore I have here a negative sign in front of this integration scheme. And this is just the integration over the line load function. And then the second term in this equation is minus FIC x minus xi, Macaulay brackets, to the power of 0. What does that mean? It means that I have to add all discrete forces which are acting, and any positive discrete force leads to a negative shear force, so a jump in the shear force function to the negative, and vice versa. So a negative discrete force leads to a positive jump in the shear force function. That is the reason why I had here this minus before the sum of all forces. Sum of all forces means all discrete forces that are acting have to be included, and they are acting at a specific position xi. By this, the power of 0 in the Macaulay bracket, that means if I have a position which is lower than xi, so the argument within the Macaulay brackets is negative, then I do not have to include these forces. But if the argument within the brackets is positive, that means my x is bigger than xi, I have to include the forces, and the argument positive to the power of 0 is just 1. So that would mean if my x is bigger than xi, I just replace the expression with the Macaulay brackets by 1. If it is lower than xi, I just delete the complete expression, so I would replace in the Macaulay brackets by 0. If I make then a second integration, so integrate over q of x to get to the bending moment function, I do not have to use a sign change, so just make a positive integration to integrate over this q of x. By this integration, if I have some linear function or quadratic function, so polynomial function for the capital Q of x, I would increase the polynomial order by 1. And then the second term in this formula says I have to subtract all discrete moments which are acting in our system. This could be external moments or bearing moments. Once again, at their specific position xj, where they are acting. And this is once again used with the formulation of the Macaulay brackets. To the power of 0 means, once again, I have a discrete function, a jump function. That means if I choose position xj is lower than the position where the moment is acting, I do not have to take them into consideration. If I look at a position which is bigger than this xj, I have to consider them, and I would then just replace the Macaulay expression by 1. For the drawing of the graphs, I do not want to go into detail right now. We will see this during the problems we are solving, but that is very important that we look at our problem statement. We can generate the small q of x function, and by integrating over small q of x to get capital Q of x, and a second integration to get capital M of x, we can draw the graphs of these functions, and we have to consider all boundary conditions as well as discrete moments or discrete forces which are acting on our system.